Hi guys, and welcome back to this virtual lecture course on Classical Mechanics and Relativity. I'm Dr. Andrew Mitchell, and in this lecture we'll be using the Lagrangian formalism that we developed in the previous lectures and applying it to special relativity as well as to the theory of electromagnetism. The general strategy in this course is to introduce you very quickly to some of the basic concepts and ideas, and then apply it to different areas of physics to really make those connections. And then once we've done that in the next few lectures, we're going to return back to basics and look in detail at how the theory is formulated. We'll be doing that then in more mathematical rigor. In these lectures, I just want to give you a flavour for the kind of things that we can do in this subject. So in this lecture, we're going to be using the principle of least action and the Euler-Lagrange equations of motion that we discussed in the previous lectures, but we'll be generalising this beyond Newton's second law. We'll basically be incorporating into it Einstein's special theory of relativity. And we'll do this by using both the principle of least action together with the principle of relativity. When we do this, we'll see that the action has to be something that is the same to all observers. It's a relativistic invariant. And this has special consequences, and it will basically allow us to derive a relativistic Lagrangian. And once we have that, we can very quickly derive some important results, for example, Einstein's famous E equals mc squared. So having devised a relativistic version of the Lagrangian formulation, we'll then be able to apply that to electromagnetism, which of course involves electromagnetic radiation which moves at the speed of light. There is a theory where we really have to use Einstein's special theory of relativity, and in fact, of course, that was the theory to which Einstein first developed the theory of relativity. When we apply that, we'll be able to devise a relativistically invariant Lagrangian for electromagnetism, and we'll be able to see that this reproduces the Lorentz force describing both the electric and magnetic parts of electromagnetic force. So that's in this lecture. Let's get down to work. In the first part of this lecture, I want to build upon the work that we did in previous lectures and generalize the concept of Lagrangian mechanics to the case of special relativity. So we're going to generalize from the non-relativistic classical mechanics of Newton, that's basically Newton's second law, to classical mechanics incorporating special relativity from Einstein. So let's just recap what we did in the last lecture. We considered the principle of least action, which tells us that the correct classical path is the one with the minimum action. That is a condition ds is equal to 0, where the action s is the integral over time of this thing L, where L is the so-called Lagrangian. If we were to use the condition ds is equal to 0 with the definition of the action s as it's written here, then we would generate the Euler-Lagrange equation of motion, which is an alternative and more powerful formulation of Newton's second law. We showed in the last lecture that to recover Newtonian mechanics, we have a specific form of the Lagrangian. It is the kinetic energy minus the potential energy. If we use this definition of L in the definition of S, and then use this condition ds is equal to 0, we recover Newton's second law, but written in a more generalized way. Okay, so the question now is, how do we incorporate the effects of special relativity, and in particular, what is going to be the analogue of Lagrangian in our relativistic world? So what is our expression for the Lagrangian L when we incorporate the effects of special relativity? This is going to be called a relativistic Lagrangian, and we'll be able to see very quickly, using the Lagrangian framework, that we can quickly obtain some interesting results when we have the relativistic Lagrangian. In particular, I'll show you that in a couple of lines of algebra we can obtain the famous E equals mc squared. So that's what we're going to do in the first part of this lecture. We're going to study relativity in much more detail in the second part of the course. This is meant to just be a light introduction. It's going to be a sketch of some of the basic ideas that we'll return to later. So before we consider special relativity, let's go back to basics and consider different coordinate systems, vectors within those coordinate systems, and invariant quantities. We'll do this, first of all, in three-dimensional space, and then we're going to generalize it to four-dimensional space-time. So first of all, let's consider 2 points in space. Imagine here I draw a graph with x and y coordinates, and I have 2 points, let's call them 1 and 2 for the sake of concreteness. I can write a vector that goes from 1 to 2, and that's a separation vector, if you like, in this space. Let me call that vector delta r. This delta r is a vector corresponding to the difference in the coordinates of points 1 and points 2 in, or I should say, along the x, y, and z directions. This is in Cartesian coordinates. Good. Now let's consider rotating our coordinate system. So here you can see that I've rotated my axes from x and y, that's the black dotted lines here, to a new pair of axes called x primed and y primed. And they're obtained from the old ones simply by rotating through this angle theta. Now notice that my physical points 1 and 2 are in exactly the same position as in the original setup. So that the physical points, our points in space, have not changed. I'm simply rotating our coordinate axes. So the question is, what is the separation vector between 1 and 2 in our new coordinate system? Well, staying with this notation, let's call this delta r vector primed. And we're going to describe this in terms of the separation between the points along the x primed axis, which I'm calling delta x primed, the separation along the y primed axis, I'll call that delta y primed, and the separation along the z primed axis, which I've not drawn, called delta z primed. This vector, comprising these 3 numbers, is not the same, obviously, as our original vector, delta r, in the unprimed coordinates. And you can see that immediately from the example that I've drawn, because in this particular example, the y primed coordinate difference between points 1 and 2 is 0. You can see that I've drawn the x primed axis parallel to the vector delta r, such that the delta y primed is equal to 0, and delta y primed wasn't 0 in the original vector, and so we can immediately see that these 2 vectors are definitely not the same. In particular, the delta x, delta y, and delta z separations are not the same as the delta x primed, delta y primed, and delta z primed. So we have 3 numbers to specify the separation along our axes in 3-dimensional space. And the point is that these 3 numbers do depend on our choice of coordinate system. Now this might seem pretty obvious, but I want to labour this point because it's important for what follows. Now there is, however, a combination of these numbers that is independent of our choice of axes. And you can guess what it is. It's, of course, the distance between points 1 and 2. There is a physical separation between those points that does not depend on how we position our x and y and z axes. So how is the distance between these 2 points related to delta x, delta y, and delta z, or for that matter, delta x primed, delta y primed, and delta z primed? Well, we use Pythagoras' theorem. So this physical distance in 3-dimensional space between the points, which I'll call delta s, is simply the modulus, or the length, of the vector delta r, which is, of course, the modulus, or the length, of the vector delta r primed. So first, let's consider delta s squared. That's, of course, going to be the square modulus of the vector delta r, which we can in turn write as the dot product of the vector delta r dotted into itself, delta r dot delta r. And we know how to compute dot products for vectors. That's clearly delta x squared plus delta y squared plus delta z squared. So if I want to know the distance, I just want delta s, so I take the square root of this. So now you can see why I said this is the Pythagoras' theorem. It's just the square root of the sum of the squares. And that's what I get when I use the vector delta r, but I argue that the distance between these 2 points doesn't depend on the coordinate system. Therefore, the length of the vector delta r is the same as the length of the vector delta r primed. And that gives us this interesting relation that the sum of the squares, delta x squared plus delta y squared plus delta z squared, is equal to the sum of the squares delta x primed square plus delta y primed squared plus delta z primed squared. So even though the individual components of the vectors do depend on the coordinate system, there is an object which is invariant, and this is the distance between the points. Okay, so what's all this got to do with special relativity? The point here is that the dot product is something that's coordinate free. It doesn't depend on our coordinate system. At the very heart of special relativity, as we'll see in the second part of the course, is this idea that there's another invariant quantity in four-dimensional spacetime called the spacetime interval. This will be an object that is invariant to rotations in space and also in time. So in special relativity, we have things called events in the four-dimensional spacetime, rather than just points in three-dimensional space. So what is this event? Well, we say that something happens here at this time, and something else happens over there at that time. So in special relativity, we have four coordinates for the events. We have 3 plus 1, 3 space dimensions and 1 time dimension. We need to specify 4 coordinates to specify our event. The main result of special relativity is that we can define an invariant interval in this four-dimensional spacetime. And this object I will again call delta S. Let's actually consider delta S squared as before. And this is defined as being delta x squared plus delta y squared plus delta z squared as for the separation, the real space physical distance between 2 points in three-dimensional space. But then there's an extra term in 4 dimensions minus c times delta t squared, where c is the speed of light. This result and much, much more will be derived and discussed from scratch in the second part of the course. But for now, let me just dangle it in front of you and we'll explore some of the consequences of it. So this object I've written down here is the space-time interval. And the important point is it's invariant. And what I mean is that one can rotate or translate the coordinate systems, or one can adopt different inertial reference frames, and yet this object will be the same in all reference frames. So we see that this result for the space-time interval for delta S squared generalizes Pythagoras' theorem to 4 dimensions, with the 4th dimension being time, and entering with this funny minus sign here. And also you see the speed of light entering as a constant factor there. So the whole essence of special relativity is that this delta S squared is a relativistic invariant. It's the same for all observers in all inertial reference frames, even though delta x, delta y, delta z, and even delta t, the difference in time, might separately be different for the observers. This quantity is the same for all observers. Now, the important thing is that the action, S, must be a relativistic invariant, and that means that it's the same for all observers in all inertial reference frames. Why would that have to be the case? Why would the action have to be a relativistic invariant? Well, if the action is the same in all reference frames, then it means that all observers will calculate the same action for any given path. In particular, everyone in all different reference frames will agree on the path that has the least action, and hence everyone will pick the same classical path chosen by nature by using the principle of least action. And this is the principle of relativity, that all inertial observers experience the same physics. If they are to experience the same physics, it means they must all agree on which path has the least action, and therefore they must all agree that the action is the same in all cases. The action must be something that is the same for all observers. So, by combining the principle of relativity that the same physics arises for all observers, and the principle of least action, that the physical path is the one with the smallest action, we conclude that the action must be the same for all observers. Okay, so we know that the action is a relativistic invariant, but what is this relativistic action? Well, we already found one relativistic invariant. It's this so-called invariant interval. Delta s squared is delta x squared plus delta y squared plus delta z squared minus c delta t squared. And if we were to send the separation between these different events in four-dimensional space-time to 0, we'd obtain an infinitesimal version of this. Let's call that ds squared. And we obtain that by sending delta x to dx, delta y to dy, delta z to dz, and delta t to dt. So we're considering infinitesimals along the x, y, and z directions, and an infinitesimal time step, dt. So we know that the total action must be something that we can split up into tiny pieces and sum them up along the path. And that implies that the action is linear. It means we can sum up all of the individual contributions. So if you imagine that we have our usual graph of position and time, and we consider some particular path, we know that we can divide up the time up into tiny pieces and consider the action along a tiny time step, which we call ds, and we know that we can get the total action by summing up all of these tiny steps ds. So we cannot use directly ds squared as a relativistic action because this is not linear. It would mean that as we reduce the time step, the contribution from each component would get smaller and smaller and smaller. What we need to do is to get the total action to sum up ds, not ds squared. That will ensure that as we send delta t to the infinitesimal dt, and therefore we sum from delta s, we replace that sum by the integral of ds, it ensures that the result will converge. So what should we pick for our relativistic action? Well, one candidate is just to square root this object, delta s squared, and then sum that up. So let's try this, and we'll see where it gets us. Let's try an action s that is, let's say, proportional to the integral of the square root of ds squared. So that's something that's linear. It is manifestly a relativistic invariant because it depends on only ds squared, and we know that ds squared from here is the same in all reference frames. And I've thrown in here for generality a proportion constant. We'll come back to that later. Okay, so let's explore the consequences of this. It seems a bit odd that you would have an integral of the square root of an infinitesimal squared. Usually you're used to seeing integral dt, integral dx, and so on. You're not used to seeing the integral of the square root of dx plus dt squared, for example. So how do we treat this? Well, let's just play with this and substitute in the expression for ds squared and see what we get. So we have k times the integral of the square root of dx squared plus dy squared plus dz squared minus c squared dt squared. So all of that is square rooted. So what I can do is take out a factor of dt squared from that square root, and that's going to leave us with something that looks rather suggestive. It's going to give us dx by dt squared plus dy by dt squared plus dz by dt squared, and then just minus c squared. The dt squares cancel. And then I have this factor of dt squared that I've taken out of the square root, so I'm just left with the factor of dt. So this is now looking much better because I have the integral dt of something.
And what is that something? Well, inside the square root here, we have objects like dx by dt, dy by dt, and z by dt. They are the velocities along the x, y, and z directions. And the sum of the square of the velocities along the x, y, and z directions is simply the total velocity squared. And so, this is very nice, because we have the integral of the square root simply of v squared minus c squared, and then the integral dt. So we're integrating now over time. Now, can this be correct? We just kind of guessed this, we're trying it out, and we see that there's actually a problem. The action has to be a real number. That's what we started from. But this object here is clearly not a real number, because we have the square root of v squared minus c squared, and the velocity, v, must always be less than the speed of light, c, according to special relativity. So this object will always be negative, and then we're square rooting it to obtain an imaginary number. So this guess that we've had here is not quite right. Actually, what we want to do is use a different action. We want to use, as our original guess, the square root of minus ds squared. So let's go back to the beginning here and replace this by the square root of minus ds squared. So I'll erase this and write in square root of minus ds squared. And following all the minus signs through, we'd obtain the following. Okay, so by ensuring that the action is real, we've introduced this extra minus sign throughout these equations, and the final result would be some proportionality constant k times the integral dt of the square root of c squared minus v squared. So this object looks much more like something we can deal with. We look at the velocity of the particle along the trajectory it takes and integrate square root c squared minus v squared along that path, and that thing is then the action. In the end, of course, what we want to do is let the action s be equal to the integral of the Lagrangian dt, and therefore we can just read off what the Lagrangian is within our guess here, and the answer is that it's simply k times the square root of c squared minus v squared. Okay, so how do we know that this guess for the relativistic Lagrangian is correct? We know that it is relativistically invariant, but why would this give us the right physics? Well, one thing that we can do is to consider the non-relativistic limit and verify that the old Newtonian mechanics is recovered in that limit. So what do we mean by the non-relativistic limit? Well, what we mean, of course, is that the velocity v of our particle is much, much less than the speed of light. And in that case, what we're hoping for is that we can recover the non-relativistic Lagrangian, and the non-relativistic Lagrangian is, of course, the kinetic energy minus the potential energy. But let's now consider a free particle. And what I mean by a free particle is that the particle is not subjected to any forces, so there's no potential in such a system. So for a free particle, the potential V is equal to 0, and therefore the non-relativistic Lagrangian is actually simply the kinetic energy T, which for a single particle is just half mv squared. Okay, that's the result that we're expecting in the non-relativistic limit. So let's just simply take our guess, essentially, for the relativistic Lagrangian, which is some constant k times the square root of c squared minus v squared. And let's just show that this recovers the non-relativistic Lagrangian when v is much less than c. So how do we go about doing that? Well, we just simply use a Taylor series expansion in the small parameter v over c. So the first step is to pull out a factor of c squared from inside the square root. That's going to give me k times c into 1 minus v upon c squared. And that's all square rooted, or put another way, to the power of 1/2. Now, since v upon c is very, very small in the non-relativistic limit, v upon c is much, much less than 1, I can treat this v upon c squared here as a small parameter and do our Taylor series expansion. That means that I can write that this is equal to k times c into 1 minus a half of k upon c squared plus corrections which are of order v upon c to the power of 4. And if v upon c is very small, then v upon c to the power of 4 is very, very small, and we're going to neglect those corrections. And that means that I can write approximately that the relativistic Lagrangian can be written in the non-relativistic limit, v much less than c, as k times c into 1 minus a half v upon c squared. And if I just write that out, I get a constant term, k times c, and then minus k over c v squared. And this quantity here is supposed to be equal to a half mv squared. And that actually tells us what this constant k is. It tells us that this constant k must be equal to minus mc. And if we use this, we get that the relativistic Lagrangian becomes minus mc squared plus a half mv squared as v over c goes to 0. And this is an important result because it tells us that the Lagrangian here recovers, the relativistic Lagrangian that we guessed, recovers the usual Newtonian classical Lagrangian for a free particle without any potential of a half mv squared. If we use this expression for the relativistic Lagrangian with a k that's just some constant minus the mass times the speed of light, both of these things are constant. But we also see something else. We see that there's this minus mc squared in here. This minus mc squared is a constant factor, so it doesn't actually affect the principle of least action. So the fact that I have a non-relativistic Lagrangian of a half mv squared, and in the non-relativistic limit, our relativistic Lagrangian has this extra term, that actually doesn't matter. And that's because when we minimize the action using the least action principle to find the correct classical path, if all paths have an added constant on, which is minus mc squared, then we're still going to select the correct minimum path. If all of the paths are just shifted up by this amount minus mc squared, then that doesn't affect our minimization procedure. So we see that in the relativistic world we get this extra constant, but it doesn't affect our selection of the classical path. However, in the full relativistic Lagrangian, we see that this term is important. And finally, this is rather suggestive, we have an mc squared here. You might be thinking E equals mc squared. Well, of course, that's related, and we'll get to that in a moment. So we've derived an expression for the relativistic Lagrangian of a free particle without any potential. So if you want the full Lagrangian, including forces due to potentials, then we simply have to subtract from this the potential. Let me call that u to avoid confusion with v being velocity here. So we simply take the relativistic Lagrangian of the free particle and subtract from it the potential to obtain the full Lagrangian. And before I continue, why don't I write this equation in a slightly different way? Let me pull out a factor of c squared from that square root there, and I'll write the prefactor as minus mc squared into the square root of 1 minus, and then I would obtain v upon c squared. So that's how I'll prefer to write this equation in the following. So let's explore some of the consequences of this. Of course, we're going to return to this in a lot more detail later. I just want to quickly sketch some of the basic ideas resulting from this expression that we've derived. So one thing that we can immediately get is the relativistic momentum. which we obtain from the Lagrangian in the usual way by taking the derivative of the relativistic Lagrangian, the partial derivative, with respect to velocity. And this is very simple to compute. We simply get m times the velocity over now the square root of 1 minus v upon c squared. And I would suggest you try that yourself just to verify that you get the same result. And the interesting thing about this expression, of course, is that on the top here we have m times v, which is the non-relativistic momentum. And so I can write this as some factor, let's call it gamma, times the non-relativistic momentum. And this therefore defines this quantity gamma, which is 1 over the square root of 1 minus v squared upon c squared. And for those of you who've seen this before, you will recognize this gamma factor as the Lorentz factor. The Lorentz factor is equal to 1 in the non-relativistic limit, and it becomes large when the velocity tends towards the speed of light. So it's basically quantifying relativistic effects. Okay, so that's already an interesting result. What about the Hamiltonian? Well, we know from the previous lecture that we can obtain the Hamiltonian from the Lagrangian, and we do that through the Legendre transformation. And so in this case, the Hamiltonian H is given by the relativistic momentum times the generalized velocity v minus the relativistic Lagrangian. That's the expression we had in the previous lecture. So let's just write it out. We would get mv squared upon the square root of 1 minus v upon c squared. That's the first term, and now we need to subtract off the relativistic Lagrangian. I'll just consider here a free particle, and that's going to give me plus mc squared into the square root of 1 minus v upon c squared. Okay, so what to do with this? Well, we can actually combine these two terms. We play the usual game of standardizing the denominator, which we can do by multiplying the second term by this factor here on the bottom of the first term, and that simply gives us mv squared over square root of 1 minus v upon c squared, and then plus mc squared into 1 minus v upon c squared over the same factor. And that allows us to add these two terms, but we see something interesting happens because we get a cancellation. In this first term we have mv squared, and in the second term we have mc squared times minus v upon c squared. And so the c squareds cancel, and I'm going to get minus mv squared. So that will cancel with this first term. So this term cancels with this piece, and we're left with simply mc squared over the square root of 1 minus v upon c squared. Using this parameter gamma, which we identified previously, which is this so-called Lorentz factor, I can write this as gamma mc squared. And in turn, I could absorb that factor of gamma into a new definition of a relativistic mass. And then I would obtain that the Hamiltonian H is equal to the relativistic mass times c squared. And of course, the Hamiltonian is equal to the total energy, as we discussed in the last lecture. And so this quantity is equal to the energy. And so what we have is that the energy is equal to mc squared, where the mass in question is the relativistic mass. So we've derived an expression E equals mc squared, which works for a particle moving at a given velocity v, and the mass is something which is a relativistic mass, and we see that this relativistic mass basically increases by the factor of gamma as the velocity increases. If we were to look at a stationary particle, or a particle in its own rest frame, then we would find simply E equals mc squared. And in this expression, the m is the rest mass, the usual thing that we would call mass. And so without very much effort at all, within the relativistic Lagrangian framework, we've obtained Einstein's famous E equals mc squared. Okay, so I don't want to say much more about that now. We're going to cover special relativity and the consequences of all of this in much more detail later on in the course. At this stage, I just wanted to introduce you already to some of the results and sketch some of these interesting ideas. Okay, so let's consider now an interesting example and application of all of this to electromagnetism. These lectures are of course not about electromagnetism, but I want to briefly cover this example to really illustrate the power and generality of these ideas. Now, the full theory of classical electromagnetism is, of course, famously a relativistic one. In fact, it is consideration of electromagnetism, as described originally by Maxwell, that led Einstein to come up with his special theory of relativity. And he basically did this by thinking about light, which is an electromagnetic effect, and considering aspects of relativity as applied to electromagnetism. Let's see how far we can get with some of the basic ideas that we have in our toolbox already. Because we're talking about electromagnetism, which involves light, and light travels at the speed of light, we really have to consider a relativistic Lagrangian formulation when talking about electromagnetic effects. So we'll consider an electromagnetic Lagrangian, L subscript EM here, and we're going to break it down into the relativistic Lagrangian for a free particle, which I'm calling L rel free here. So this is the one we considered previously. And then minus the potential, and this potential will be to do with the electromagnetic forces. So as before, our relativistic free Lagrangian is given by m minus mc squared into the square root of 1 minus v upon c squared. So this object is going to give us the relativistic kinetic energy, basically, of a particle. And the potential is described by this second term, u here. So first of all, let's consider a single charged particle in a static electric field, which is this vector field E. Now, of course, we can write this in terms of a scalar potential for the particle. The potential energy is then Q, the charge on the particle, times this phi, which is the scalar electric potential. And of course, this is defined such that the electric field is recovered as minus the gradient of this scalar potential. This is, of course, the situation in electrostatics. And the force acting on the particle is, of course, just the charge on the particle times the electric field. This is just the definition of the electric field in terms of the scalar potential and the electric part of the Lorentz force. So with that, it looks like we're in a position to write down our electromagnetic Lagrangian, or at least a part of it, pertaining to electrostatics. We have the relativistic free Lagrangian minus q times phi. But is this expression really correct? If so, it would imply that we could write down an action for electromagnetism, which would be the integral of the electromagnetic Lagrangian dt. And of course we can break that down into the two pieces, the relativistic free Lagrangian of the particle dt minus q times the integral of the scalar potential phi times dt. But there's a big problem with this because it's not relativistically invariant. And it's very important, as argued previously, that the action be a relativistic invariant. And that's because we should use the principle of least action to determine the correct classical path. And the principle of relativity tells us that all observers should have the same classical physics, and so that implies that the action should be a relativistic invariant. And this action that I've written down is not a relativistic invariant. How do I know that? Well, let's look at this first term. We have the integral of the relativistic free Lagrangian dt. Well, we know that is relativistically invariant. We constructed it explicitly with that in mind. The problem is this second term. To understand this, we need to go a bit deeper into special relativity. Obviously, we're going to study all of this in a lot more detail later on, but let me just introduce you to some key concepts now. In special relativity, we have 4 coordinates. We have 3 spatial dimensions and 1 for time. And we saw earlier that we can write a spacetime event in this 4-dimensional spacetime, and we can make a vector which is involving the time coordinate and the spatial coordinates. This thing is called a 4 vector because there are 4 components, and one of these components is the time. Actually, it's the time multiplied by the speed of light, so it's dimensionally consistent. So let's denote this event 4 vector by capital X. I can make from this an infinitesimal dx, which is, of course, just c dt, dx, dy, and dz. Now, we know that a relativistic invariant is the spacetime interval. That's the thing we previously called ds squared, and that is like a generalized dot product of our dx. So I'll leave out the actual dot here to remind us that this is a generalized kind of dot product, and it has components which are dx squared plus dy squared plus dz squared, as from Pythagoras, and here comes the difference, minus c squared dt squared. Okay, so this object is a relativistic invariant, and we obtained it by doing this generalized dot product of this thing called a 4 vector. Now, in the theory of electromagnetism, we will have an electromagnetic potential, which again has 4 components, and we call this the electromagnetic 4 potential. And the 4 components involve the scalar potential that we were just discussing. Actually, it's 1 over c times this thing. And then the spatial parts, the spatial coordinates, involve the x, y, and z components of the magnetic vector potential. So let's call this quantity A. And let me just remind you, of course, that for magnetostatics, at least, when we have time-independent electric and magnetic fields, the magnetic field B is just obtained as the curl of this vector potential, where this A vector here has 3 components, which are precisely AX, AY, and AZ. Okay, so with this 4 potential A, which has these 4 components now, the first of these being actually the electric scalar potential, what we can do in principle is form a kind of dot product involving our 2 4 vectors, the A and the X. Specifically, let's consider A dx. What will this give us? Well, if we just follow the same rule as before, we'd have ax times dx plus ay times dy plus az times dz. But then we have this extra funny minus sign coming in, and so instead of phi dt, we have minus phi dt. Notice that the factors of c and 1 over c cancel. So it's these dot products between 4 vectors, these generalized dot products, that are relativistic invariant quantities. They're the things that don't depend on the reference frame. So what we see from here is that this kind of objects that I've written down here is the same to all observers, but a single component of it is not. And what we have in the guess here for our relativistic action involves a phi dt term. That's just one part of this whole object here. It's not the full thing. And so, as a guess, what we'd imagine is that if we want a relativistic action, we would have this piece minus q phi dt, but then we should also have q times these other terms. And so let me just write that down. So our relativistic invariant action for electromagnetism would involve the part corresponding to the relativistic free particle. We have a piece corresponding, as we know it must, to the electrostatic potential. And then we argue that the principle of relativity implies that we have to have other terms in here as well, and they must be specifically q times the integral of ax dx plus q times the integral of ay dy plus q times the integral of az times dz. Only this full thing could be something that is relativistically invariant, and that object can be written in a slightly more concise way as minus q integral of phi dt plus q times the integral of the magnetic vector potential A dotted into the velocity v dt. So here I did a trick. I divided and multiplied each of these terms by dt, and that thereby I was able to pull out an overall factor of dt, and then I would have dx by dt, dy by dt, dz by dt, and then the components of velocity, vx, vy, vz, and then you can combine those neatly into this simple dot product, a vector dot v vector. And these are regular 3 vectors and the regular dot products that we know and love. And I wanted to do this because I've now been able to write this whole thing as the integral dt, and therefore I can write this whole thing as the integral of a Lagrangian for electromagnetism dt, where the electromagnetic Lagrangian involves a free piece, which is just for the particle moving around without any potential. And then we have a piece corresponding to the potential, which I'll call UEM, where this UEM is simply Q, the charge of the particle, times the scalar potential minus the vector potential dotted into the velocity of the particle. And of course, it turns out this is the correct result. And this is very interesting for several reasons. One, we can basically argue, just from very general ideas, what the form of the electromagnetic potential should be within this Lagrangian framework. And furthermore, when we use this expression within the Euler-Lagrange equation of motion, we'll be able to basically pull out the force on the particle, and we'll see that this potential actually reproduces the entire Lorentz force, which gives a force of Q times the electric field plus velocity crossed with the magnetic field. So these expressions are consistent, they're internally consistent with each other. There's a second interesting thing about this equation, which is that we have a potential here which apparently depends on velocity. And I told you earlier that our potential shouldn't depend on velocity, they should only depend on the positions. So here we have a slightly more generalized concept of the potential, which we'll return to later on in this course. One final thing is this is not actually the full action for electromagnetism, because we also need a piece in our electromagnetic theory corresponding to the electric and magnetic fields themselves, the energy contained within the electric and magnetic fields themselves. But when we add that to our action to obtain the total action for electromagnetism, we can then define a Lagrangian, and when we use the Euler-Lagrange equations of motion with that Lagrangian, we recover Maxwell's equations of electromagnetism. So this is something that we won't cover in this course. However, the full theory of electromagnetism, which builds upon the machinery that we're developing here, is considered in a separate lecture course on electromagnetism, and that's available also on my YouTube channel. So you can go and check that out, and you can learn how to apply the principle of least action and the Lagrangian formulation to electromagnetism in detail in that course. Okay, so I don't want to say anything more about the electromagnetic Lagrangian at this stage. Instead, let's change direction now and consider a totally different application of the Lagrangian formulation and the principle of least action, which is to quantum mechanics. That will be the topic of the next lecture, and we'll use the principle of least action to make a connection between classical mechanics and quantum mechanics. We will see how classical mechanics emerges out of quantum mechanics, and the tool we'll use to understand that will be precisely the principle of least action.